There is an object at the bottom of every ship that most people will never see. It sits below the waterline, hidden beneath the hull, turning slowly in the dark, cold water. It has no equal in engineering, no replacement when it fails, and no margin for error when it is built. It is the propeller, and on the largest vessels crossing the world's oceans today, the propeller is one of the most precisely manufactured objects ever produced by human hands. Building one takes months. Getting it right takes decades of accumulated expertise. And the process, from raw metal to finished blade, is as extraordinary as the machine it powers. This is how a ship propeller is made, and why every single step of that process matters more than most people will ever know. Before understanding how a propeller is built, understand what it must do. A ship's propeller converts engine power into thrust. The rotating blades push water backward. That ship's propeller reaction drives the ship forward. Simple in principle, extraordinarily complex in practice. The propeller blades are not flat. They are twisted, each one a precise three-dimensional curve called a hydrofoil section. As the propeller rotates, each blade generates lift through the water in the same way an aircraft wing generates lift through air. That propeller blade generates lift becomes thrust. That thrust becomes movement. The angle of that twist, called the pitch, determines how much water the propeller moves with each rotation and at what efficiency. Too steep and the engine strains against resistance it cannot overcome. Too shallow and the propeller spins without generating sufficient thrust. The pitch must be calculated precisely for the specific vessel and the specific operating profile of that ship. On a large container ship, the propeller operates at between 80 and 100 revolutions per minute. At that propeller speed, the tips of the blades move through the water at velocities approaching 40 meters per second. The stresses on each blade, bending, vibrating, we can tell it, or listen or caress and vibrate. Everything about how a propeller is built flows from those demands. A ship propeller is not made from steel. Steel corrodes in salt water. It is vulnerable to the microscopic implosions, called cavitation, that occur when a propeller blade moves fast enough to create vapor bubbles in the water around it. Those bubbles collapse with explosive force against the blade's surface. Over time, steel cannot withstand that assault. The material of choice for nearly every large commercial propeller in the world is nickel aluminum bronze. It resists corrosion, it absorbs the shock of cavitation without cracking, it is strong enough to carry the structural loads of propulsion, and workable enough to be cast, machined, and finished to the tolerances that precision demands. The composition of that alloy is not approximate. The ratio of copper, aluminum, nickel, iron, and manganese is controlled to exacting specification. A deviation in the alloy chemistry changes the material properties in ways that only thousands of miles from any repair facility. The raw materials arrive at the foundry. They are weighed, tested, verified, and only then melted. The casting of a large ship propeller is one of the most demanding foundry operations in industrial manufacturing. The mold is built first. For a propeller that may span 9 or 10 meters in diameter, the mold itself is enormous. Constructed from bonded sand, shaped precisely to the geometry of the finished propeller, and propeller assembled in sections that must align to tolerances measured in fractions of a millimeter. The molten alloy, heated to over 1,000 degrees Celsius, is poured into that mold in a single continuous pour. Interruption is not an option. A pause in the pour creates a cold joint, a weakness in the metal that renders the entire casting unusable. The pour for a large propeller can involve over 100 tons of molten metal, moving in a controlled, precise flow managed by experienced foundry workers who have done this work for decades. The mold is then left to cool, slowly, deliberately. The cooling rate affects the grain structure of the alloy, and the grain structure determines the mechanical strength of the finished blade. Rushing the cooling process compromises the material at a molecular level in ways that no surface inspection will ever detect. When the mold is finally broken away, after days of controlled cooling, what emerges is a raw casting, recognizable as a propeller, but nowhere near finished. The raw casting is structurally sound, but it is not a propeller yet. The surface of a cast propeller blade is rough, marked by the texture of the sand mold, by minor irregularities in the pour, by the natural imperfections of a process working at the edge of what metal and heat and human skill can achieve together. Every one of those imperfections must be addressed, because at sea, surface finish is not an aesthetic consideration. It is a performance and safety requirement. Rough blade surfaces create turbulence in the water flowing across them. Turbulence reduces efficiency. It accelerates cavitation, It increases vibration, and vibration transmitted through the propeller shaft into the hull is felt by every person and every piece of machinery on the ship. The finishing process begins with large grinding and milling machines. Computer-controlled cutting tools remove material from the blade surface in precise passes, working toward the final design geometry. But the machines can only go so far. The final finishing is done by hand. Skilled propeller finishers, craftsmen with years or decades of experience, work across the blade surface with hand tools, checking the geometry against precise measurements, feeling the surface with their hands, listening to the grinder as it moves across the metal. They are not following a simple procedure. They are applying judgment, the kind of judgment that only comes from experience with a material and a process that cannot be fully automated. When the surface meets specification, when every measurement across every blade falls within the required tolerance, the propeller moves to final inspection. A ship propeller does not leave the foundry on trust. It leaves on proof. The inspection process for a large marine propeller is thorough, systematic, and witness. Every blade is checked for defects. Now for the ultrasonic test. Results are in spec. Final polish looks good. Inspection complete. Signing off. Their approval is not a formality. Without it, the propeller does not ship. Every blade is measured at dozens of defined points across its surface. Pitch, rake, skew, thickness, chord length. Each dimension is checked against the design specification recorded. Ultrasonic testing checks the internal integrity of the casting, looking for voids, inclusions, or discontinuities in the metal that no surface inspection can reveal. The propeller is then statically balanced. Each blade must carry equal weight distribution around the hub. An imbalanced propeller creates vibration that grows with rotational speed. And at sea, that vibration damages shaft bearings, wears seals, fatigues structural connections, and makes life on board deeply uncomfortable for crew and passengers alike. Finally, the surface is polished to its finished specification. The smoother the blade surface, the less drag, the less turbulence, the greater the propulsive efficiency. On the largest propellers, the final surface finish is measured in micrometers. Only then, after every measurement, every test, every signature from every inspector, is the propeller released. Getting a finished propeller from the foundry to the ship is itself a logistical operation of significant scale. A large propeller, weighing 80 to 130 tons, cannot be moved by conventional transport. Specialist heavy lift vehicles carry propeller from the foundry. Cranes of significant capacity lift it into position, and the journey from manufacturer to shipyard can cross countries and oceans before the propeller ever touches water. At the shipyard, the propeller is fitted to the propeller shaft in dry dock. A precision operation that requires exact alignment between the propeller boss and the tapered shaft end. The fit is hydraulic. The propeller is driven onto the shaft under controlled oil pressure, creating a mechanical interference fit of enormous holding strength ship's propeller. Bolts alone do not hold a ship's propeller. The interference between the metal surfaces does. When the ship is launched and the dry dock flooded, the propeller enters the water for the first time. And during sea trials, the first full power runs of the completed vessel, every element of the propulsion system is tested against its design specification. Speed, thrust, vibration levels, shaft power, fuel consumption. The propeller is performing under real load for the first time. Speed, and the engineers and naval architects watching those results are measuring the real-world performance of months of work against the calculations made at the very beginning of the design process. When the numbers align, when the ship performs as designed, the propeller has done its job. And it will continue doing that job, submerged and unseen, for the next 20 to 30 years of the vessel's working life. Most people who travel by sea never think about what is turning beneath them. They feel the movement of the ship. They see the wake stretching behind the hull. But the blade driving all of it, silent, working continuously in water that is cold and dark and indifferent, remains invisible. That blade was designed by naval architects who spent months calculating its geometry. It was cast by foundry workers who poured over 100 tons of molten metal in a single unbroken operation. It was finished by craftsmen whose hands and judgment produced a surface that machines alone could not achieve. It was inspected by surveyors who signed their names to its quality. And it was installed by engineers who understood that the tolerance of a single measurement would determine how well that ship performed for the next 3 decades. There is no mass production here, no shortcut, no acceptable approximation. Every propeller is a singular object, and it does that job in conditions that would destroy almost anything else. That is what it takes to build the blade that moves the world. If this video gave you a new respect for the engineering and the people behind it, subscribe for more real maritime stories.